Have you ever just looked up at the sky and wondered, how do you get a planet? I mean, a whole world like Earth or a giant like Jupiter from, well, basically nothing. From just this huge, empty looking cloud of gas and some microscopic dust? Well, today we're doing just that. We're going to build a planet from scratch. And along the way, we'll uncover the incredible cosmic puzzles that scientists had to solve to figure out the recipe. And just to wrap your head around the sheer scale of what we're talking about. 13 orders of magnitude. That means you're starting with a dust grain smaller than the width of a human hair, and you're ending with something thousands of kilometers wide. It's a growth spurt so enormous, it's almost impossible to imagine. And for the longest time, we had absolutely no idea how it could possibly happen. Okay, so the story always starts here, with what's called the nebular hypothesis. The basic idea is simple. Right after a star is born, it's surrounded by this massive spinning platter of leftover gas and dust. This is the protoplanetary disk. Think of it as the cosmic nursery, the warehouse of raw materials where all the planets are going to be born. So all our ingredients are there, just swirling around in this disk. But how do you get them to actually come together? You know, the first idea seems super intuitive, but it also turned out to be our first major roadblock. It sounds so simple, right? Little tiny dust grains just gently bump into each other, they stick, and then over millions of years, voila, you get a planet. Kind of like cosmic dust bunnies clumping together under your bed. But when scientists actually ran the numbers, they realized the universe is nowhere near that gentle. Right? Let's get into this, because this is where our nice, simple story completely falls apart. Scientists ran into what they called the meter-size barrier. And honestly, it was a planet killer of a problem. In fact, it had two deadly parts to it. Okay, so here's the first issue. In that big protoplanetary disk, the gas doesn't actually orbit the star as fast as a solid rock does. The gas is kind of like a big crowd. It has its own pressure pushing outwards, which helps support it. But a solid object, like a growing boulder, is all on its own. It has to move at the exact right speed that gravity demands. And that means the boulder is always moving faster than the gas around it, creating this constant, inescapable headwind. And that headwind? It's a killer. For an object that's about a meter across, the drag is just catastrophic. It's like slamming on the brakes. The object loses energy, and it starts to spiral inward, right toward the star. And the timescale for this is, well, it's terrifyingly short. About 100 years. That's it. Before it has any chance to grow bigger, it's completely vaporized. This was a total dead end for the theory. And as if that wasn't bad enough, here's the second deadly part of the barrier. This chart here is basically a map of what happens when two particles collide. You don't need to worry about the exact numbers, just look at the colors. See the green areas? Those are the sweet spots where things stick together and grow. But look at all that red. In those huge zones, collisions are destructive. The particles either just bounce right off each other, or even worse, they shatter into even smaller pieces. So this was the puzzle, right? Your building blocks are either getting sucked into the star by a cosmic headwind, or they're just smashing each other to bits. It seriously looked like planet formation was impossible. How could nature possibly get past this? So how did we solve it? Well, it turns out nature doesn't always play by the simple rules we think up. It uses a loophole, a really clever collective hack to basically cheat the system. And this simulation illustrates the solution perfectly. It's a process called the streaming instability. And what happens is, instead of acting alone, particles start to clump together. As they gather, they create their own little shield, dragging the gas along with them. This reduces that deadly headwind for the whole group. It creates this amazing feedback loop, a kind of cosmic traffic jam, where more and more particles pile into these dense filaments that you see forming here. Now here's the crucial part. Once those clumps get dense enough, their own collective gravity takes over, and bam, they collapse directly into objects that are 100 kilometers across, what we call planetesimals. So nature doesn't bother trying to slowly build through the meter-size barrier. It takes a massive leap and just jumps right over it. Problem one, solved. But of course, in science, solving one mystery almost always reveals another one. We now have these planetesimals, the building blocks, but there was a brand new problem, especially if you want to build a giant planet like Jupiter, a ticking clock. I mean, a gas giant is, by definition, mostly gas, and all that gas has to come from the protoplanetary disk. The problem is, observations show us that these disks don't last very long. Within just 3 to 5 million years, all that gas gets blown away by the star. That means a giant planet has an incredibly tight deadline. It has to build a massive core, we're talking 10 to 20 times the mass of Earth, and then grab all of its gas before the well runs dry. In that old model of just having these 100-kilometer planetesimals randomly crashing into each other over millions of years, the simulations were clear. It's just way, way too slow. You could never build a core fast enough. The gas would be long gone before you even had a seed to collect it. It was another dead end. This huge dilemma led to one of the biggest revolutions in modern planetary science, a totally new theory that took our old villain, that pesky gas drag, and turned it into the ultimate hero of planet formation. It's called pebble accretion, and the idea is that the biggest planetesimals don't just wait around for other big things to hit them. Instead, their gravity starts to influence these massive swarms of tiny, centimeter-sized pebbles that are drifting by. And that same gas drag that created the death spiral from meter-sized rocks, it now works in our favor. It slows the pebbles down just enough that they can't escape the core's gravity, and they spiral in to get captured. It's like a cosmic vacuum cleaner, just hoovering up material. And the effect is just stunningly efficient. This graph shows you the result. That red line there is a growing core out in the outer solar system. Instead of taking tens of millions of years, it can grow to 20 Earth masses in less than 2 million years. It's this explosive, exponential growth that just demolishes the deadline. This was the breakthrough we absolutely needed. So, when you put it all together, these two huge ideas, the streaming instability to jump that first barrier and pebble accretion to win the race against time, they give us this powerful toolkit, a toolkit that can explain not just our own solar system, but the incredible variety of planets we're now finding around other stars. It's almost like we have a recipe book now. If pebble accretion is super effective and happens early on, you can make a gas giant. If it's a little less efficient or maybe happens a bit later when there's less gas, you might end up with a super Earth. And then in the inner solar system, where pebbles are smaller, you form these planetary embryos that then spend tens of millions of years colliding in these giant impacts to form rocky worlds like our own. So we've gone from these seemingly impossible problems to these really elegant solutions that explain so much. But every single new planet we discover out there around another star presents a brand new test for these theories. We figured out the broad strokes of how to build a planet, but the universe is, without a doubt, full of more surprises. The next cosmic rulebook is just waiting out there for us to find it.